Hello and welcome back to another episode of I don't know what I'm calling this yet. I'm Rob Simpson, and today we're going to discuss the Equal Area Criterion. What is the Equal Area Criterion? I don't really know. Equal Area Criterion. So the Equal Area Criterion is how you tell if your generator is going to survive a fault. You have your curve of power that the generator can provide, going from 0 to its peak and back down to 0 on the other half of its sine wave. And then you have the power you're demanding, or PM, as we will use in our calculations. We just want to make sure that the area below PM on the curve is equal to the area above PM when the protection kicks in. The criteria for all of this actually corresponds pretty directly to your connection to the load. So there's a bunch of different ways to do this, depending on if you lose all connection to the grid, you lose one grid connection, you lose 2 of your 7 grid connections. All of these different types of failures all change how you respond. We're actually going to only cover a very simple aspect of it. So let's have at it.
For this calculation, we need to make sure that the power generated during our fault can be dissipated within the generator before the point of no return. When we do this calculation, we're looking at just a few different curves and how they intersect. PM is the power demanded from the generator. We'll call this a 1 per unit because the math is easier when we use per units. So what we have here is PM intersects with our generator's total curve, or the pre-fault max. At this position, we have our delta 1 angle. On this graph, we have 2 more curves as well. We have our post-fault maximum power and our during fault maximum power. For this calculation, we will need to verify that the area from PM to the fault maximum curve from angle delta 1 to delta critical is equal to or less than the area under post-fault max to PM from angle delta critical to delta 2. This sounds a little complicated, but it's really not so bad. We're just trying to make sure that the extra energy generated can be dissipated within the recovery curve of our generator. So I have listed our maximum angles, and we have our PM is 1 pu, our frequency at 50 Hz, our P fault curve is 0.4 pu, and our P pre-fault is 1.8 pu maximum, with our P post-fault at a 1.3 pu maximum. These are just the maximums of our sine waves that are just superimposed on each other for this graph. So when we move on to the calculation, we'll find that delta 1 is equal to the inverse sine of PM over P pre-fault. In this specific example, it's 33.8 degrees or 0.59 rads. Our delta 2 is PM over P post-fault, inverse sine, and then because we want to verify that we're on the right half of the sine wave, we have 180 minus this angle. So in this case, it's 180 degrees minus 52.3 degrees, which equals 127.7 degrees or 2.23 radians. Now that's the easy part. What gets complicated is when we calculate delta critical. Now we can use inspection on the graph above to see that the integral from delta 1 to delta critical of PM minus P pre-fault sine delta d delta equals the integral from delta critical to delta 2 of P post-fault sine delta minus PM d delta. What we are calculating here is not actually delta critical. We're calculating the maximum delta critical possible for this specific generator and fault conditions. So any delta critical less than is actually acceptable. The math here breaks out to the cosine of delta critical equals PM times delta 1 minus delta 2 plus P pre-fault cosine delta 1 minus P post-fault cosine delta 2 divided by power pre-fault minus power post-fault. In this case, delta critical is 55.8 degrees or 0.9738 radians. As long as the time it takes for a response from our systems is at or less than 55.8 degrees on the sine wave, our generator should function properly. And there you have it, the equal area criterion. It's really not that difficult of a concept to cover. The problem comes from when you start discussing how your grid and everything interacts during faults. You have to figure out how much power you're delivering and how much power you have lost access to during and after the fault. Once you figure those out, you can just set up a bunch of different equations to figure out your fastest response time required. And there you have it, the basics of the equal area criterion. Good luck!
Thank you for watching, and feel free to share what you've learned.